Welcome back to this lecture series on pulse width modulation for power electronic converters. So, we have been going through, this is the 14th lecture, we have been going through a number of modules here. In the first module, we looked at various kinds of power electronic converters, different topologies, DC-DC converters and DC-AC converters like 2-level, multi-level and all those we saw there. And after that, we just had an overview of just the voltage source converter, what we are looking at here as voltage source converter, we just had that. And after that, we looked at the purpose of pulse width modulation, certain introductory ideas about pulse width modulation, why you require pulse width modulation. Basically, you want to control the fundamental voltage and you also want to control the harmonic voltages such that they are not very high and their undesirable effects are kept as low as possible. So, we try to do that here. And in this fourth module, we have been looking at low switching frequency PWM methods for this knob. That is essentially what you have our voltage source inverter, we are going to switch them and we are switching them at a frequency which is very low. So, right now we are taking only 2 switching angles per quarter cycle, or the switching frequency is only about 5 times the fundamental frequency. And with this, we are trying to understand how the fundamental and harmonic voltages are related to the switching angles. That is the whole burden of our the recent past few lectures. So, as I was mentioning, we have been considering only 2 switching angles per quarter. The waveform has quarter wave and half wave symmetries. So, what it has is in essence it has about 5 switching cycles within a line cycle now. So, it is switches at 5 times the fundamental frequency. If the fundamental frequency is 50 hertz, the switching frequency would be 250 hertz now. So, you only have 2 angles alpha 1 and alpha 2, the other angle here being fixed at 0, that will be one other angle switching at 180 degrees now. So, with only 2 angles, we are keeping the problem as simple as possible. We have been trying to understand how the fundamental and the harmonic voltages are related to switching angles, so that we can achieve the necessary fundamental voltage, at the same time we can mitigate the harmonics and their ill effects. So, we were looking at how the fundamental voltages vary. This is how they vary, that is along this line on the alpha 2 versus alpha plane, any point on this line gives you 0 fundamental voltage and any point on this line gives a 0.2 per unit fundamental voltage, where 1 per unit stands for the fundamental voltage equal to the square wave operation, the 6-step operation of the inverter now. So, we have been doing all this through hand sketches. We have been trying to calculate the values and sketch them by hand in the past few lectures, because we want to get a good idea of what is really happening there. Now that we have gained certain amount of insight, we can start using some computer programs for plotting them. Let us say you plot this constant V1 contours now. So, what I have done here is I have plotted for different values. Here this is for V1 is equal to 0. So, this entire line is V1 is equal to 0. You can choose any value of alpha 2 comma alpha 1 on that particular line. The resultant would be a PWM waveform whose fundamental component is 0, right. Then the next one that you have is 0.2 and the next line that you have corresponds to 0.4 per unit fundamental voltage. Then this is 0.6, this is 0.8 and this is 1.0. So, your fundamental voltages are varying in this fashion now. If you want 0.8, it in effect it means you can choose any of these points. Which point you choose, that would depend on which harmonic you want to be lower or whatever you can. So, the first objective of controlling the fundamental voltage is easily attained from here. So, from V1 is equal to 0.8, any of this on this line, you can choose any point on the line. Which point you can decide based on the harmonic content, etc. now. So, which is the principal harmonic? The fifth harmonic would be the principal harmonic. In the third, in the 3-phase inverter, if there are any third harmonics in the pole voltages, they will get subtracted. VRO as some third harmonic, VYO will have the same third harmonic, and VRO minus VYO when you are doing in the line to line voltage, that effectively gets cancelled out. So, we do not have to worry about the triplet harmonics as we saw earlier. We will only first worry about the fifth harmonic now. And this is the specific problem of fifth harmonic elimination, which again we discussed in the last class. We want the fundamental voltage to be equal to the desired value. The alpha 1 and alpha 2 should be such that the fundamental voltage is equal to the desired value. At the same time, the alpha 1 and alpha 2 have to be such that the fifth harmonic has got to be 0. This is the problem of fifth harmonic elimination. You have 2 equations, simultaneous equations, but they are nonlinear transcendental equations. You use a numerical iterative procedure to solve. What we are trying to do is, rather than just using a procedure, we are trying to understand what is happening behind the scene. That is what we are trying to do here. So, we plotted all the V phi is equal to 0 contours last time. We tried plotting various values, plugging in several numbers of alpha 1 for example into this equation and calculating the corresponding values of alpha 2, and we found how the contours were coming up to be. And now the same contours are now plotted using a computer program. So, this is a V phi equals 0 contour. This is another contour, that is along this line also you have V phi equals 0. This contour is nothing but the same fellow shifted up by 72 degrees, because 72 degrees is 360 by 5, that gives the periodicity for the fifth harmonic. So, the same contour when it shifted to the right appears here, and it is only a part of it appears here, because this is our area of interest. Why? This line marks alpha 1 is 0, we cannot have alpha 1 less than 0. So, alpha 1 is equal to 0 is one boundary, and alpha 2 equals 90 is another boundary. Again we have a constraint that alpha 2 has to be greater than alpha 1, this is alpha 2 equals alpha 1, and so we have to operate only in the top right angle here now. And within the top right angle also you have, this is 0 per unit fundamental voltage, this is 1 per unit fundamental voltage now. And on this side you are going to, you will still get some waveform, you may get something like 0.4, 0.5 per unit that you might want, but it will have a different phase as I was mentioning in a previous lecture now. So, we are essentially going to operate not even within the top triangle, we are going to operate within these two blue lines marked here as 0 per unit and 1 per unit now. So, these are the fifth harmonic contours that are of interest to us now. So, if you want to choose any value of fundamental voltage, let us say I want to choose 0.5. If I choose V 1 is equal to 0.5 and I plot 0.5, V 1 is equal to 0.5 on this, I see that it intersects as 2 points. These are the solutions for the fifth harmonic elimination problem. So, along the line I can choose any point firstly to achieve the necessary fundamental voltage of 50%, that is 50% of the square wave, right. Now, along this I have two different points, at these 2 points I am guaranteed to have fifth harmonic to be 0. We do not know what is the seventh harmonic, we do not know what would be the 11th harmonic, we would know what is about 13th harmonic, we do not know what would be the overall things now. But one thing that we can certain is, let us go back to the slide. If you look at the slide here, so you see this at this point. Now, let me mark this point as A and let me mark this point B now. We will see a little later that A and B are equally good as far as fifth harmonic is concerned, both are eliminating fifth harmonic. But you will find that B is better in terms of seventh harmonic. After fifth harmonic, the most dominant harmonic is actually the seventh harmonic. So, it is probably better to choose B, as we will see later now. Firstly, what we have to see is, sometimes your equations are possible, you can get multiple solutions out of them. You may start solving a particular problem and your friend may also solve the same equation. You may come with one solution, he may come with a different solution. Now, why is that? Because this equation at in certain ranges can give you multiple solutions, and this is what we are trying to see now. So, what are the ranges? Now, at 0.5 for example, it gives two different solutions. The fifth harmonic elimination, the same fifth harmonic elimination problem, if I consider a different fundamental voltage of 0.9 per unit, gives only one solution. It does not intersect with the other V phi equals 0 contour on this side. It does not intersect here, it only intersects here. And let me call this point as C. So, point C is the only solution when it is 0.9, you have nothing else. Whatever is the 7th harmonic, whatever the 11th harmonic, whatever the 13th harmonic at that point, you just have to accept it. If you say that I want V 1 is equal to 0.9 per unit and V 5 should be 0, then this is the only solution for you when you are using only 2 switching angles per quarter cycle now. So, let us see that this, there is this, so some range in which you have multiple solutions and some range you have unique solution, and there is also certain range where you have no solution at all. For example, you take V 1 is equal to 1 per unit and you take anything close to that, something like 0.98 per unit. That will be very close to this line and that may not intersect on this red contour also, it may not intersect with this also. That is what we will see in the next one, we will see the ranges now. First, let us say if I take alpha 1 is equal to 0, what I am getting is the, for V 1 is corresponding values of alpha 2 I am getting as 60 and 12 degrees. That is, for alpha 1 is equal to 0, this is 12 degrees, this is 60 degrees, and this is one of the curves now. Then along this line you have alpha 2 is equal to 90 degrees. So, when I use alpha 2 is equal to 90 degrees, the corresponding values of alpha 1 are 60 and 84 degrees. So, I go here. So, this is 60 degrees alpha 1, this is 84 degrees now. So, this is what we have. So, along this curve let us see how fundamental voltage varies, and along this curve how the fundamental voltage varies now. If you are starting from here, the fundamental voltage is 0. As you move past in this curve, the fundamental voltage goes on increasing, and at this point it reaches V 1 is equal to 0.8 per unit, and I have plotted that 0.8 per unit line here. If your fundamental voltage increases beyond 0.8, there is not going to be any solution out of this particular curve now. So, up to 0 to 0.8 per unit, this is 0 here and this is 0.8 here, you have one solution as we saw before. And if you are looking at this curve, this is 0 here and this is some 0.96 per unit here. So, if you are moving starting from this point and you are moving all the way here, the fundamental voltage goes on increasing. The fifth harmonic is always 0, the fundamental goes on increasing, and you reach when you are reaching here, you get something like 0.96 per unit, and beyond that 0.96 per unit there is no solution now. So, 0 to 0.8 you have two solutions, and between 0.8 and 0.96 we have one solution, and beyond that you have no solutions. So, this is what we are coming up here. So, 0 to 0.8 you have two solutions, and this is one, and there is sometime no solution now. Now, let us take the counterpart of the seventh harmonic elimination problem, and before that let us look at these the two options, how you can look at them, how do you really implement them. So, the stored waveform PWM, it comes from them. That is what you are trying to do is, let me just explain now. So, there are two solutions here. Now, I am focusing on one of the solutions which I have marked in green here. So, what I want to do is, I would start from this point and I move along this curve, and I have reached alpha, I am sorry, I have reached alpha 2 is equal to 90, and at alpha 2 is equal to 90, along alpha 2 equals 90 itself I move and go and reach the end point. So, what is that? This curve along with a straight line is a locus of a point which starts from V 1 is equal to 0, sorry, this is V 1 is equal to 0 and this is V 1 is equal to 1 per unit. So, this curve starts from there and goes there. So, this is how we define a PWM technique, if you could recall in a previous lecture. A PWM technique can be defined as any contour, I mean any locus of a point which starts from one of the points on V 1 is equal to 0 contour, or any V 1 is equal to V minimum contour, and ends at V 1 is equal to 1 or V 1 is equal to V max. That is all that we want to do now. So, any line that you can draw, you can just draw a straight line from here to here, and you can call that a PWM technique. You can draw some wavy line from here, you can call this as a PWM technique. Now, in this case we can call this as a PWM technique. This green curve can be called as a PWM technique. What does it essentially say? It only gives the relationship between alpha 1 and alpha 2 here, and V 1 varies as you move along the curve. So, along the locus of the point V 1 varies monotonically. You start from here and you go on doing that, V 1 goes on increasing, it reaches 0.8 here, and from here it goes on again further increasing, it goes to 1 now. So, along this locus it increases monotonically. So, if you want to implement a PWM method, what you can do is you can just save this curve. What is that curve? It has some alpha 1 and alpha 2 defined. At every value of alpha 1 and alpha 2 on this curve there is a V 1 now. So, let us say if you want to implement a PWM method, you can save this as a lookup table, and hence the name stored waveform PWM. When you want V 1 is equal to 0.4, then V 1 is equal to 0.4 could be some point like this, could be, I am sorry, V 1 is equal to 0.4 could be a point like this now. At that point you have some alpha 1 and alpha 2. What those values are, you can pre-compute them and you can store them in a lookup table and you can output them. And this is the idea of what is called as a stored waveform PWM, and that is what we are trying to look at today. So, the selective harmonic elimination methods are one variety of stored waveform PWM. Now, you can store this green color curve in a lookup table and you can output it as required now. Alternatively, it is not necessarily that this green curve, you can also use this other curve. You can also use this other curve now. Incidentally, I have called this as PWM 1, that is PWM 2, that is okay, we have been shifting here now. So, instead of using that curve, what I am trying to do is I am using this green curve here, and now this green curve. So, if I move along this green curve, it starts from 0 and the fundamental voltage goes on increasing monotonically, and it finally reaches 0.96 roughly, and beyond this point fifth harmonic elimination is not possible. But I want to still control the fundamental voltage, therefore, I move along this green line to the origin now. So, this green line is again a PWM technique, and with this PWM technique the fifth harmonic is eliminated all the way from 0 fundamental unit to 0.96 per unit, and the fifth harmonic is not eliminated between 0.96 and 1, there is certain amount of fifth harmonic is always there now. Similarly, with the other curve, that if you had chosen this one, fifth harmonic would not be there between 0 to 0.8 and it will be there now. But between 0.8 and 1 there will be certain amount of fifth harmonic certainly there now. It is also possible for you to start with this curve and follow this curve up to some point and jump back from there to here with the same V1, says at V1 is equal to 0.6 or 0.7, some intermediate point, you can jump over here and you can follow this curve and you can move over there now, that is also possible now. So, as I was mentioning, PWM is a locus of a point on this alpha 2 versus alpha 1 plane, and the locus starts from V1 is equal to 0 or V1 is equal to minimum, V minimum, and ends up at V1 is equal to 1 or V1 is equal to maximum contour. So, this is what you can do. So, this is another example of a stored PWM waveform now. These stored PWM waveforms are stored waveform methods are targeted at eliminating the fifth harmonic now. So, you can also think of the other method of eliminating seventh harmonic voltage now. It is a similar exercise, but you will see that there are differences now. So, this is V1, you want decide V1 to be equal to your desired V star. At the same time, V7 you want it eliminated instead of V5. Mathematically, it is the same procedure, 2 equations, 2 unknowns. So, you go about solving it iteratively, you have a good starting solution, you can converge faster and you go about doing that now. We are trying to see a graphical approach as we have been doing. So, now this V7 is equal to 0 contours, we plotted them again by hand in the last few classes. Now, you can see that I have plotted them here now. And many times the way I plot it would look like a semicircle, and I kept on telling you that it is not exactly a semicircle. Now, the point you can very clearly see that point, it is not exactly a semicircle now. It is actually flatter at the middles and it is more curved at these edges now, the 4 corners, that is what you can see there. And you can see that between V5 and V7 they are appearing more frequently, because the spacing the periodicity in case of V5 equals 0 was 360 by 5, that is 72 degrees. Here it is 360 by 7, that is something like 51.4 degrees. So, they you find closer, and you find the other 2 curves also appearing prominently. In the case of V5 they appeared somewhere at the corners. Now, the other 2 curves are also appearing more prominently here now. So, this is V7 is equal to 0 contour now, and any point here you will have V7 is equal to 0. Again on any point here you will have V7 is equal to 0. And interestingly, this V7 is equal to 0 contour starts at a point here, here. At this point the fundamental voltage is not equal to 0. It again ends at a point where the fundamental voltage is not equal to 1. That is not surprising, because when V1 is equal to 1 it is square wave operation, and a fifth harmonic or seventh harmonic cannot be 0, right. So, but it is interesting to note that there are certain V7 equals 0 contours which do not start at V1 is equal to 0, they start at some other point. This is something we could not see when we plotted V5 equals 0 contours. This is one reason why one would like to plot V1 is equal to V5 equals 0 sometime, V7 is equal to 0, V11 equals 0, V13 equals 0, etc. These are exercises that will tell us will make us understand the relation between the switching angles and the harmonic voltages better. Now, you have this now. On the other hand, you have this contour now. This point here V1 is equal to 0, at this point also V1 is equal to 0. So, you start, and if you start from this point and move along this contour here, okay, you start from here 0, it goes on increasing, at some point it reaches a peak, the V1 becomes something like 0.87 or so, and beyond that point it goes on reducing, and at this point it becomes 0. And on this side of the contour you still have V7 is equal to 0, you get fundamental voltage, but it is negative. What do you mean by that? You will get certain fundamental voltage, but the phase will be reverse of what you will get on this side. That is what is going to be the case now. So, if you see, if you are considering V1 is equal to 0, there are 2 points available for you here and here. These 2 points eliminate seventh harmonic for you while guaranteeing whatever V1 you want. You take any V1 which is small like 0.02, 2% or 3%, you are going to have something very close here. So, you will have 2 different solutions possible now, correct. So, which of the solution you will choose? In both the cases you can get the desired fundamental voltage, in both the solution you can get V7 is equal to 0, but you might probably want to choose a solution where V5 is also low, may not be 0, but at least low. you will see that this point V phi is 0 and anything close to this point V phi is fairly close to 0. On the other hand, if you take this point, V phi is at its maximum really, and any point close to this V phi is going to be very high. We will see that little later. So, I would say that I would probably take a point here rather than take a point here when I want to do 7th harmonic elimination, if 5th harmonic is a criterion too. So, beyond certain range now. So, I am trying to illustrate this with certain specific examples. One is V 1 is equal to 0.4, excuse me, I want to take V 1 is equal to 0.4. So, V 1 is equal to 0.4 is a curve that moves like this. Let me write 0.4 on this. So, this is the 0.4 curve, I have drawn it in black. So, it does not intersect this side, but it intersects with this curve at these 2 points now. So, there are 2 solutions possible. So, for certain range starting from 0 to some number, there are 2 solutions possible. Then I am considering V 1 is equal to 0.8 and this is V 1 is equal to 0.8 I have shown plotted here. If I take V 1 is equal to 0.8 and plot that contour, it intersects this curve here and it intersects this contour at 2 different points. So, there are 3 different solutions available for you, 3 different solutions available for you. You have a choice to choose from, greater number of choice to choose from. So, one way as I said, you can probably look at what the 5th harmonic is at those points. There are 3 points available x, y, z, and you can see at which of the points V phi is the lowest and you can choose. Or you can also look at certain other criterion. As I will say talk about it a little later, you can also look at pulsating torque, that is also a factor. There are other issues that you can consider and choose one of these 3 points now. Firstly, we should be aware that options are available and what are the options available, and then evaluate the options. For evaluating the options, we should know what are the criteria that we would like to pose. So, one of them could be V phi being 0, one of them could be the weighted THD of voltage being low, other one could be the pulsating torque, let us say the 6th harmonic torque being low, etc., etc. So, now these 3 points are there in this law. Now, let me go to another value that is 0.95. If we go to this V 1 is equal to 0.95, I have intersection only here and this V 1 is equal to 0.95 does not intersect this contour, it does not intersect this contour at all, correct. Yeah. So, there is only one solution now. So, initially you had 2 solutions, and in some range you have 3 solutions, and in some range you are back to only one solution, and finally, when you are very close to V 1 is equal to 1, there is no solution. So, 7th harmonic cannot be eliminated here. So, let us delineate these ranges clearly. So, if you start along this curve and you move along this, what are the maximum values now? For V 1 is equal to 0, you have some values here, alpha 1 is 16, alpha 2 is 90, and here you have 36 and 72 degrees, that is what I have written here, 36 and 72 degrees now. So, along this curve if you move 0 to 0.87 roughly, it can give you a solution. 0 to 0.87, it can give you 2 solutions. This side of the curve can give you one solution, this side of the curve can give you another solution. So, this particular contour alone can give you 2 solutions in the range 0 to 0.87. And if you look at this and you look at what is the fundamental voltage at this point, the fundamental voltage at that point is alpha 1 is 0, alpha 2 is 42.86, the fundamental voltage is something like 0.466. So, up to 0 to 0.466, this fellow does not give you any solution. From 0.466 all the way up to 0.978, it is 0.978 here, it gives you one solution. So, this fellow gives you 2 solutions between 0 to 0.87, and this one gives you 2 solutions, one solution between 0.547 to 0.98 or so. So, from between 0 to 0.46, this is 0.46. So, excuse me. So, this is 0.466. Between 0 to 0.466 is one range where you can get 2 solutions, and then you have 0.87, this is 0.87. Between 0.466 and 0.87 you get 3 solutions now, and finally, you have 0.978. So, at this point it is 0.978, and this black curve, it is a little very close to V 1 is equal to 1 per unit. So, that between 0.87 and 0.978 you can get one solution, and when your V 1 is beyond 0.978, 7th harmonic cannot be eliminated. That is what is indicated here. You have 2 solutions and you have 3 solutions and you have 1, and you have no solutions, no solution here, right. So, let us move on. So, you can once again look at stored PWM waveform. There are several options available and I need a PWM method. How do I do? I have an inverter, I have a motor to run, let us say using a constant voltage per hertz, volts per hertz control, and I need a pulse width modulation method to do that. So, one thing that I can do is, let me just choose a green kind of color here. I can start from here. This is V 1 is equal to 0 and I can move along this curve, I can move along this curve as long as the fundamental voltage keeps on rising, maybe up to some point here. So, I would have started off with 0 and here I will have something like 0.87 per unit now. Up to this point, this contour promises me 7th harmonic eliminated, there will be no 7th harmonic here. And from here I can just move along a straight line here. I am sorry, I should have used a different color here, just a moment. Yeah, I am sorry about that. So, let me go back to the contour that I wanted to say. So, I start from 0, I follow this contour, and from here I can come like this and end here. I can come and end like this now. So, are you able to see the green curve? This is a PWM method. This green curve is a PWM method. I can save this as a lookup table and output this. Alternatively, let me use another color. Shall I say yellow? Now, I can start from here. I can go along this curve, I can come back and join this V 1 is equal to 1. So, this yellow curve is another PWM technique. This also guarantees me, the necessary fundamental voltage, and it guarantees me 7th harmonic would be 0, starting from 0 to something like 0.87 per unit. Beyond that, it does not eliminate. Okay. So, this is another one. So, the green curve can be stored as a lookup table or the yellow curve can be stored as a lookup table now. Alternatively, you can also consider this method. Let me use red itself here. I can start from here, I can move along this curve and I can move along this whatever red curve and go back here. This red is another PWM method now. So, I am giving you 3 different examples of PWM methods and these are stored waveform methods. You can store them in lookup table and you can output them and you can use them now. So, they all can give you fundamental voltage ranging from 0 to 1 per unit. But in the case of this green and the yellow, the 7th harmonic will be eliminated all the way from 0 to 0.87, but if I use the red one, it is not so. Between 0 to 0.47 it is not eliminated, it is eliminated only between 0.47 but up to 0.97 or so. I can also move along one of them and jump over to the other one and do this, such things are possible. I am just trying to indicate some examples for you now as to what can be done now. So, these are stored waveform methods and you can go about doing, and the green is probably the most preferred solution. I can easily tell you why, because the range is very good. It starts from 0 and goes all the way up to 0.87 just like the yellow also does. But in the case of yellow curve, as you can see here, 5th harmonic is very high. So, the 7th harmonic may be eliminated, but the 5th harmonic is very high. This would result in a very high pulsating torque, as we will see a little later now. Just briefly look at that. So, this could be very bad in terms of 5th harmonic being bad and in terms of the 6th harmonic pulsating torque being very high in the motor drive. So, this could be particularly bad now. So, you may not want to use it. So, you have options, when you have options you should know how to weigh various options and go about doing them, and these are all examples of stored PWM waveforms now based on 7th harmonic elimination. So, selective harmonic elimination is one kind of stored waveform. It is not necessarily, you can also do many other kinds of waveforms you can come to, there are several other PWM methods now. This V5 equals 0 and V7 equals 0 gives you a very good idea. If you plot them, they give you some kind of good idea as to how you can go about designing your PWM method. So, now we have only 2 switching angles, we want to see how best to go about doing it. So, we have done this exercise of plotting V5 equals 0 and V7 is equal to 0. Now, let me start off. Let me use some 2 different options. One option, let me call it as the green option, and the other option, let me call it as the yellow option. What is this green option? I would start from V1 is equal to 0, right. What is a PWM method? it is a locus of a point which starts from this V 1 is equal to 0 contour and ends up with V 1 is equal to 1, let us say. So, now I will start my green one PWM technique, I will start from there, and another PWM technique which I would probably say the yellow one, I can start from here. What are the advantages of these 2 points? At these 2 points you see that the 5th harmonic is 0, you also see that the 7th harmonic is 0. It is supposed to be, it should be so, because while this entire blue line guarantees you V 1 is equal to 0, this blue line guarantees you V 1 is equal to 0, these 2 are the only points on the blue line that guarantees that all the harmonics are also 0, 5, V5, V7, V11, V13 etc. are also 0, because the waveform is a third harmonic square wave here and it is also a third harmonic square wave as I told you in a previous lecture now. So, the 5th, 7th, 11th, 13th harmonics do not exist. So, not only 5th and 7th which are shown here, 11th and 13th also do not exist. So, both are equally good options now. Now, let me say I want to slightly increase that V 1 is equal to 0 is not a point at which you would operate. We are trying to understand that V 1 equals 0 mainly to understand the issues related to V 1 is equal to say 2% or 3% or small amount of voltage now. Now, let me say, let me go back to this. I want to use something like V 1 is equal to like 2% or 3% now. So, if I were here, what I would choose, that curve can really be going somewhere like this now. This is a small voltage now. I can choose some point here, alternatively I can choose some point here. You see that it makes better sense to choose this point over this point. Let me choose the green point over the yellow point. Why is that so? At the green point, if I choose this green point, I am both V5 and V7 are kept reasonably low, whereas if I choose this yellow point, this may also give me the same fundamental voltage. I am reasonably closer to V5 equals 0, little farther too, but I am far away from V7 is equal to 0. Now, let me just finish it up. Is it the green? Yeah. Now, let me say I just take a straight line moving like this. I just take a straight line moving like this. On the other hand, with the yellow line, let me just draw a line like this. The green line is a PWM method and the yellow line is also a PWM method, as I have also mentioned before. The green is good in certain respects, because as the fundamental goes on increasing, you are not straying away very far from V5 equals 0 contour or V7 is equal to 0 contour. You are not straying very far away. So, for a up to certain substantial value of fundamental voltage, this curve moves along very close to V5 equals 0 and V7 and guarantees you low values of V5 and V7. So, those are the 2 principal harmonics. So, the currents are going to be dominant, like V5 and V7 are more dominant over V11 and V13 in terms of their currents. V11 and V13 face higher harmonic reactances than V5 and V7 do. So, if you can keep V5 and V7 low, what is the problem? So, you can consider a method like this now. Again, what you can do is you can move on here. If you consider the same yellow line, what happens? You are moving away and away from V7 goes in the other direction, but your curve is moving in the other direction. So, your V7 starts increasing very quickly, though V5 may be reasonably low, but it is increasing. So, it is going to lead to a substantial amount of V7 and also substantial amount of 6th harmonic pulsating torque. So, that is an issue there now. So, you can also consider certain variants. So, this is how you can look at when you draw all these curves, you know what necessary, and actually this point is a good point. This point is a good point, because V5 and V7 are both equal to 0 now. So, if you can look at a trajectory which passes through that point, that is also fine, and this point guarantees you 0 pulsating torque, because the pulsating 6th harmonic torque is determined by the 5th harmonic voltage and the 7th harmonic voltage. If they are both equal to 0, 6th harmonic torque should be 0. It is actually a good point to operate in. So, you can look for any curve that goes through that or goes close to this and things like this now. So, several possible contours you can draw, infinite number of contours. You can start from any point on V1 is equal to 0 and you can choose any point on V1 is equal to 1, and from that point to this point there are several contours, again infinite number of contours. It basically tells you that the infinite number of PWM techniques are possible, but not all PWM techniques are equally good, right. How do you choose those good techniques now? So, not only control of fundamental voltage in terms of harmonics also, that has been the burden of our thing now. So, if you look at V 5 and V 7, just for example only two of them, it makes it crystal clear that these are the only 2 points which are worth operating at when you are looking at V 1 is equal to 0. When you are looking at V 1 is equal to some small number, again you need to be close to one of these 2 points, and it is better that you are close to this point rather than close to here, because if you are close to here, both your V 5 and V 7 are guaranteed to be low. On the other hand, if you are here, your V 7 could be much higher. That is the reason now. So, it gives you an idea of what to do on this now. You can also plot V 11 and V 13, and you can see, you can get a better picture of what exactly happens now. You would generally see that in your here at low modulation indices, when you are operating somewhere here, it is very good. It is something very good now. So, let me just plot V 11, V 13 and such kind of curves now. If I really plot them, you know how they would look? Most of the curves will actually go like this now. Those are loops I have indicated. This is like V 11 is equal to 0, V 13 is equal to 0 and go on. And all the curves will move tangential at this particular point now. So, at that point all the harmonics are 0. And you can see that if your locus, the PWM, the locus that the line that indicates the PWM technique itself moves tangentially to all the Vn equal to 0 contours. So, along the line the harmonic is not increasing very highly. So, that is one of the reasons. So, for at low modulation indices, almost all the harmonics are very close to 0 here now. As you will see in what is called as the minimization of weighted THD, you would get many points normally close to this now. That is, if you are operating here, your overall THD V 5 is guaranteed to be low, V 7 is guaranteed to be low, V 11 is guaranteed to be low, V 13 is guaranteed to be low, and overall the weighted THD is guaranteed to be low here at low modulation indices. That is not the same when it comes to high modulation indices. Now, let me say if I take this point here, obviously it is square wave. So, fifth cannot be 0, 7th harmonic cannot be 0, and similarly come close to higher modulation indices may not be the case now. On the other hand, if you consider anything here, you consider this band here, you consider any point here, you are assured of V 5 as well as V 7 being reasonably low, and these are high modulation indices now. If you plot V 11 equals 0, V 13 etc. equal to 0, also you will see that in this area you will see many of the Vn equals 0 contours passing here now. So, this essentially tells you that at high modulation indices, if you operate closer to this origin, in this region, you are guaranteed to get better results. Many of the harmonics could be lower. At lower modulation indices, it is better that you operate closer to this particular point. At higher modulation indices, you operate in this range now. So, if I may have to give you something indicatively, at lower modulation indices, if I take this angle, what is that? This is 60, this is 90. Both my alpha 1 and alpha 2 are within the range 60 to 90 degree. If I choose my alpha 1 and alpha 2 to be within the range 60 to 90, the lower order harmonics are likely to be much better at low modulation indices. And similarly, if I am talking of high modulation indices, it is better that I operate somewhere within this range. It is better that I operate somewhere within this range, that is 0 to 30 degrees. I have to make sure that both the switching angles are probably within 0 to 30 degrees and closer to them now. That is how you will get now. Right. So, this is basically to give you. On this, I would certainly encourage you to plot V 11 equals 0 and V 13 equals 0 contours, etc. You can certainly make use of, the way we were looking at V 5 equals 0, V 7 equals 0. It is also possible to plot for you roughly where it comes, and you can also use a computer program to plot it precisely. So, you will see what happens and how exactly it is going to come through, and you see this issue now. So, there are many PWM methods, and and it is possible to, and some of them will be better than the other. And we are trying to get some idea as to how one could design better PWM methods now. So, if you are looking at this only up to 2 switching angles, now you want to go more than 2 switching angles, because this 2 switching angle, you must realize that we took it up only as a means to improve our understanding. We just wanted to understand the relationship between the fundamental voltage and the harmonic voltage on one hand with the switching angles on the other hand. So, we kept the problem simple by only 2 switching angles now. So, what is this 2 switching angle stuff? We have been considering a pole voltage which is like this. We have been considering pole voltage VRO is like this now. This is 0 degree, this is alpha 1, this is alpha 2, this is 90 degree. This is what we have been considering. Now, if you want to consider 3 switching angles, Here VRO is switching from 0, at 0 it is switching from negative to positive. It is common to consider the switching the other way. At 0 degree VRO would normally switch in the other direction, and this could be your alpha 1, this could be your alpha 2, this is 90 degree. Alpha 1, alpha 2, I am sorry, alpha 1 it goes back, alpha 2 comes 9, and then alpha 3 and 90 degree. It is normal to use it the other way, that is at the 0 crossing your VRO will be switching from positive to negative now. So, this is for 3 switching angle problem now. So, you have alpha 1, alpha 2, alpha 3, V 1 is related to alpha 1, alpha 2, alpha 3, V n is related to alpha 1, alpha 2, alpha 3. You can do all that you want to do, the harmonic elimination. So, 5th harmonic and 7th harmonic, 2 harmonics can be eliminated with controlling fundamental voltage now. So, with 3 switching angles, 2 harmonics can be eliminated. This is the nature of waveform we will use now. Now, let us say you want to use 4 switching angles. So, what you can probably do is you go like this. So, this is 4 switching angles per quarter, alpha 1, alpha 2, alpha 3, alpha 4, and this is 0 degree. So, generally for even value, for where n is the number of switchings per quarter and it is even value, you choose this kind of a PWM waveform where VRO switches from negative to positive, and in general for the other side you will switch it the other way, alpha 1, alpha 2, alpha 3, 0, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, 90 degrees. So, for n is odd, you are using this kind of waveforms, and you can use for any value of n now. So, these are more and more switching angles now. The exercises that we did for n is equal to for 2, we can do similar exercises for n is equal to 3. We can plot, here we could plot on, for n is equal to 2 we could just plot it on a single plane, here it has to be plotted in a 3 dimensional space, but still you can use your computer programs to plot those and get an idea of how V 5 equals 0 and V 7 equals 0 contours are here, how they would be, instead of being a curve in this case, instead of being just a curve here, it would become a surface here, it would become a surface in the 3 dimensional space here, and for all these you can just formulate the equations and you can go about solving them. If you look at the selective harmonic elimination and you look at n switching angles, so you can have n number of equations. So, V 1 is equal to V 1 star is the desired fundamental voltage, this is one of your equation. Then you can go about eliminating n minus 1 harmonics, capital N minus 1 harmonics, where n is the number of switching angles per quarter. You can eliminate 7th, 5th harmonic, 7th, 11th, 13th and up to n minus 1 harmonics you can go about eliminating. You can solve all these equations, it is capital N number of simultaneous equations. These are all transcendental equations and you can solve them and you can come up with solutions now. Again you may come up with different solutions. So, sometimes it may give you but same set of equations, you may come up with one solution, your friend may come up with another solution, because one reason could be that your starting solution and his starting solution is very different. So, depending on numerical procedure and the starting solution that you take, you would converge on to one or the other kind of solutions here now. So, we are now better, we know that multiple solutions are possible and all such awareness that we certainly have. And with an idea of all this V 5 equals 0, V 7 equals 0, where are the harmonics being 0, it is also possible for us to suggest good values of starting solutions now. Okay. So, many a times if you want to eliminate all the harmonics, you can also start low. Let us say V 1 is equal to 0.5 per unit is what you want to start, you want to do. So, and all some n minus 1 harmonics have to be 0. You can also start at a point where the waveform is effectively a 3rd harmonic square wave or a 9th harmonic square wave or so on. In that case all the harmonics are anyway guaranteed to be 0 and your fundamental voltage is 0. So, once you know the solution for that, you can calculate, that is V 1 star is equal to 0, the solution is very obvious, and then you can calculate for V 1 star is equal to some small value 0.01, 0.02 and you can go about calculating. So, this can give you the solutions for various values of V 1 also. Okay. So, typically in the books you will find solutions for against V 1. Now, let me just write it down here. Now, what you will find is against V 1 different values of alpha will be plotted here, alpha 1, alpha 2, alpha 3 etc. Would be plotted against this now. I am not doing this here, you can certainly go about and doing this as an exercise, and it is available in several other references which I am going to mention now. They are all right. Okay. So, now if you move to the next point, now this is about selective harmonic elimination. That is not the only stored waveform quality. What you can do is you can go about minimizing THD. You can go about minimizing the THD. The THD is the line current. The THD in the line current is equal to the weighted THD. W stands for weighted total harmonic distortion in the voltage waveform. Now, if you see that there is a factor Vn, what is this Vn? Vn is the nth harmonic voltage. The nth harmonic voltage sees a harmonic reactance which is n times that seen by the fundamental voltage. So, you have a Vn by n factor here, and that is whole square. So, this gives you basically that I have missed out a square root on this, I am sorry. So, what you would normally have is you would have a square root on this, you would have a so this Vn by n is indicative of the nth harmonic current, and the sigma Vn by n the whole squared is indicative of sigma In squared, is a measure of sigma In squared, that is all the harmonic currents added together, the total ripple current. So, that is normalized with respect to the fundamental voltage now, and this is called the weighted THD of the voltage waveform, which is equivalent to the current THD. If you multiply the weighted THD by a factor which is roughly equal to the no load impedance divided by the block rotor impedance of the machine, you will get your current THD roughly. So, now theoretically it contains all the values of n, but you will see that at higher values of n, now the the Vn itself will be low and Vn by n will be very low. So, they can be ignored. So, I have just shown like V 5, 7, 11, 13, you can probably stop here. I mean, you can consider more values, I am just trying to tell you that n can be truncated at some point approximate here. Now, you choose your alpha 1 and alpha 2 such that they guarantee going to the same switching angles, the alpha 1 and alpha 2 they guarantee the required fundamental voltage. At the same time, they minimize this weighted THD. That is, you look at the entire possible solution of entire set of all values of alpha 1 and alpha 2 which will give you the required V1 star, and you choose that particular value which gives you minimum amount of weighted THD. That is what is called as offline optimal PWM for optimizing minimizing thing. So, you can do an offline optimization, you can calculate the optimal switching angles. So, for V1 is equal to 0.1 per unit, what is my alpha 1 optimal and alpha 2 optimal? V1 is equal to 0.2 per unit, what should be my alpha 1 optimal and alpha 2 optimal, and you can store all of them in a lookup table. So, this is again a stored waveform PWM method. So, this waveforms will give you not just eliminating fifth harmonic or seventh harmonic, they will not eliminate, but they will try to minimize the weighted THD. Fifth harmonic may not be 0, seventh may not be 0, but the overall weighted THD of the voltage waveform or the current THD or the THD of the current waveform will be very low. So, this is what is an offline optimal PWM method now. So, minimization of THD of line current or weighted THD of line voltage is what is done here. Alternatively, you can also try and minimize pulsating torque. How do you do by minimizing pulsating torque? You will have to understand what causes pulsating torque. What causes pulsating torque? Had the motor been operating with sinusoidal voltages, there is going to be no pulsating torque at all, it is going to be a steady torque. Only because the motor is operating with non-sinusoidal voltages, you are getting pulsating torque. What are the effects of non-sinusoidal voltage? The flux is non-sinusoidal and the currents are also non-sinusoidal. So, if you consider the flux, you have a sinusoidal component, you also have non-sinusoidal components. Again similarly, you consider the currents, the motor currents, they also have fundamental and non-sinusoidal. The fundamental flux and the fundamental current interact to produce the steady torque, whereas the fundamental flux and the ripple current, harmonic current produce the pulsating torque. The same way, the fundamental current and the harmonic fluxes interact to produce the pulsating torque. Also, the harmonic fluxes and the harmonic currents can interact, but they are negligible because harmonic fluxes themselves will be negligible and harmonic currents will be negligible, and their product would be much more negligible, you do not have to worry about. So, what causes pulsating torque is, one is the fundamental flux interacting with harmonic current and the other one is the fundamental current interacting with harmonic flux. An analysis can show you that the fundamental flux interacting with harmonic currents is what is really higher. So, it is really cause of harmonic current now. So, now let me say I have these harmonic currents, one is I5, fifth harmonic current. What does this fifth harmonic current do? this fifth harmonic current would interact with the fundamental flux and the relative speeds would be 6 times the fundamental frequency, and this will end up producing as sixth harmonic pulsating torque. The same way the seventh harmonic current will also do the same job. The seventh harmonic current and the fundamental flux both revolve in the same direction. They have a relative speed of 6 times the fundamental frequency. So, this I7 fellow also interacts with the fundamental flux and gives you produces sixth harmonic torque. So, both I5 and I7 are responsible for sixth harmonic torque. So, if you want T6 to be 0, ideally what you should do is make sure that I5 and I7 are 0. If you want to make I5 and I7 0, what you should do is V5 and V7 both should be 0, but it may not be possible, particularly if you are considering only 2 switching angles, it is not possible. So, if you analyze the problem clearly, you would see that T6 depends on the difference between I5 and I7. It actually depends on the difference between I5 and I7. So, if you can make sure that the difference between I5 and I7 is very low, you can make sure that the difference between I5 and I7 is very low, then you can eliminate sixth harmonic pulsation now. So, let me just change this further now. So, what is I5? I5 is basically V5 upon 5 and V7 is basically V7 upon 7. So, if your fifth harmonic and seventh harmonic are such that V5 by 5 and V7 by 7 are close to one another, then the sixth harmonic pulsating torque is reduced. I am trying to simplify the arguments, I am giving a very simple picture now. So, with 2 switching angles itself, it is possible for you to make sure that the fifth harmonic and the seventh harmonic are both close to 0, then you can get this kind of waveform that you hear now. Let us go back to the V5 equals 0 and V7 equals 0 contour, and there we will see this point now. So, here I want to point out to you that let us say this point, excuse me. So, if you say this point as I pointed out to you, T6 is equal to 0 there, T6 is equal to 0 at that point. Why is T6 is equal to 0? Because both V5 and V7 are equal to 0, and therefore, I5 and I7 are equal to 0, and therefore, sixth harmonic torque is 0 now. Now, let us say you consider a point something close to that, you consider a point something close to that. This point V5 is not 0 and V7 is also not 0. But it is quite possible that the V5 and V7 amplitudes, you have to search around that point, it is possible for you to find a point where V5 and V7 are such that V5 by 5 is equal to V7 by 7, and also V5 and V7 have the same phase. If you kind of come up with such kind of a point, then you can say that the sixth harmonic torque gets eliminated there also. Similarly, this point you have a sixth harmonic torque is 0. Why? Because V5 and V7 are both equal to 0. And you come somewhere on this line, you may come somewhere, you will get a set of points here. Along these points that you are indicating, it is the V5 and V7 are such that V5 by 5 and V7 by 7 are roughly equal. V5 by 5 is roughly equal to V7 by 7. You can get a set of points now. This is what would be sixth harmonic torque being 0 now. So, you can look at selective elimination of harmonic torque, and you can calculate the switching angles, and you can save them as a lookup table that is also stored vform PWM method. Instead of considering particular pulsating torque, instead of considering sixth harmonic torque, you can also consider the sum of all the torques, 6th, 12th, everything. You can consider the RMS torque or the peak torque, and you can try to minimize. You come up with switching angles, alpha 1 optimal, alpha 2 optimal, alpha 3 optimal, etc. that would minimize your pulsating torque, the peak value of the pulsating torque or the RMS value of pulsating torque, whatever it could be, or specifically 6th harmonic torque or 12th harmonic torque. That also can be called as an optimized PWM, offline optimized. You are calculating all these offline and you are storing them as a lookup table and using it during your implementation now. And you can also attempt to minimize the motor losses. These harmonics are causing certain amount of motor losses, increased copper losses, and there is also increased core losses. You can, if you understand the relationship between the switching angles and the motor losses, if you can express this mathematically, then it is possible for you to come up with alpha 1, alpha 2 optimal values, which will give you, apart from the necessary V1, which can also minimize the motor losses now. You should know how to express motor losses in terms of switching angles. You can also look at the total losses, which is the inverter plus motor losses now. So, if you look at the inverter plus motor losses, you should once again be able to express the total loss as a function of the switching angles. then you can minimize. You can treat this as an optimization problem and minimize, and you can calculate your alpha 1 optimal, alpha 2 optimal, alpha 3 optimal at every possible values of V 1 like 1%, 2%, 3%, 4%, save it as a lookup table and use it during the waveform now. So, that is what we have about offline optimal PWM. Here I am going to suggest some good papers which are seminal work, and there are also other papers in this area, but I am just going to suggest a few of them for you to go and read and so that you get a better understanding of this. So, these are some of the earliest papers on harmonic elimination method. Now, there is part 1 and part 2 which particularly dealt with harmonic elimination and voltage control methods. Now, these were published in the years 1973 and 1974 by Patel and Haft. So, these are among the oldest. There are still older paper here like Turnbull in 1964 etc., but I am just giving you this paper as one of the references now. So, this is all. You also have this book by Professor Holmes and Professor Lippo on pulse width modulation for power converters, principles and practice. This summarizes many of the selective harmonic elimination methods, the work that have been done over the years has been consolidated. You will find a lot of several graphs here which are very useful for you to understand what happens and things like this now. So, this I would suggest this as an additional reading too now. Then about the optimal PWM, about minimization of THD, this is a very good paper. This is one of the first papers in this topic. They calculate the switching angles in this paper. Bhuja and Indri calculate the switching angles such that the THD is minimized, or the weighted THD of the voltage is minimized. This was published in the IEEE Transactions and Industry Applications in the year 1977. So, now you continue with that. Not only minimizing THD, you can also minimize the motor's pulsating torque or the torque ripple and the speed ripple. So, this paper by Sack, Martinez and Keplinger and Caesar in the year 1985 on the same IEEE Transactions and Industry Applications deals with that. How do you calculate your switching angles such that the pulsating torque is low? That is what we were I just gave you an indication. This paper discusses all the details there. And similarly, this is efficiency optimal PWM for AC drive. So, they are trying to reduce the overall losses in the motor drive. So, the switching angles, the losses are expressed or the efficiency of the motor drive is expressed as a function of switching angles, and you try to optimize and get this. So, these are certain very useful references that I would like to suggest. So, all these are examples of the stored waveform PWM method now. This is perhaps the last lecture that we will have on low frequency PWM methods. In the low frequency, we took it up essentially to understand what we are trying to get an essence of how fundamental voltage and harmonic voltages are affected by switching angles and so on and so forth. Now, we are practically done with the low voltage things, and generally we dealt with selective harmonic elimination and all this optimal PWM. You save them as a PWM waveform, do that now. From the next lecture onwards, we will be looking at a situation where the switching frequency is much higher than the fundamental frequency. We will say probably the fundamental frequency is 50 hertz, we may look at switching frequency of 5000 hertz or so, which is 100 times the fundamental frequency. So, the way you analyze and all that could be very different when you are doing there now. So, that is what we are going to look at now. So, most of the modern methods are really like that, unless you go to very high power levels etc., you will do this here. So, in the modern context, there are certain low frequency cases where when the power level is very high, your switching frequency is low. Therefore, the ratio of switching frequencies, the fundamental frequency is low. And the other situation is the switching frequency is high, but the modulation frequency is also high in case of high speed motors. And that is again a situation where the low frequency methods we studied will be helpful. Next lecture onwards, we will be focusing on the high frequency methods, and thank you for your interest and hope that you will continue to follow these lectures. Thank you very much.